record. Can you go this way? Yes. So anyway, so imagine this is a system that, we fix it together. I made a mistake, you guys fix it, and all of this, right? What is this system is doing up-down counting. Do you agree? And then, we add this extra feature of the, you can inject in which digit, whatever value it is, right? And then it's still counting and so on. Now, this up-down counter, it has here the up-down switch, and it has here the switch for what? For the enable, disable, the whole entire counting. Do you agree? This one is no longer needed, or it can be needed actually if you want. You understand what I'm saying? If you want it to be have a luxury of automated system doing the enable, disable for the counter, you can just make like an AND gate, right? That's enable, and then the output of the sequence detector, right? So what is the circuit of the circuit detector will be? It will be the following, right? You already have here two inputs. One is completely serial, and the output here also serial, and that will be the enable here, right? Then you already have here what? Pattern, right? This pattern, it doesn't matter how it looked like. Let's say, the pattern here is 1 1, like 1 1 1, for instance, right? Is there any overlap, or there is no overlap? You can add it also in your circuit if you want, but imagine, I think in the request I said, we don't need overlap, right? It's without overlap. Let's take it easy. So basically, without overlap. Do you remember the lecture that I described apart? Hello.
Yeah.
Yeah.
Yes. So basically, this is basically what you need to do. So you need to build this one literally, like what I built based on the specification I give you in the lab, and then you will be thinking about how can you connect this like that, right? Then you have a luxury. If this switch is on, then this guy will be taking the order, because think about it. If one ended with X, the output will be X, right? That makes sense?
Yeah.
Then that will make it what? Counting. Sounds good?
Yeah, that makes sense. Maybe another question we had was, in your video, you mentioned that like when it detected the sequence, it would start incrementing. So did you mean that, or did you mean for it to increment by 1 every time it detected a sequence?
What were I saying? I'm sorry. Oh, I forgot to say something. I'm sorry to interrupt you. And also, I said, I want to use the memory, right?
Correct.
So basically, what you are doing here, you already have a kind of mechanism with PTR, right? Like a pointer, right? And then you already have here the addresses, right? That you're gonna push it with switches. Do you agree? Then every time you would select, you will make a combination that will be recorded here, right? So end of the day, you already have. I don't remember how many locations I asked it in the video. I think I asked it for 8 locations or something, right? So in that case, it's a 4-bit, 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 right? So then you need to do what? You need to do parallel serializer. So that means you need to make something in serial, right? Like you're gonna have like a kind of register. One of the dummy way is actually to have a big register like this. You take the first part and you load it here, the second part you load it there, the third part you load it there, and the first part you load it here. It's whatever. And then this by itself, every single cycle you're gonna push from the left to the right by 0. And that guy will be going into the detector itself. I mean, this is one of the ways. There is actually more smart ways you can do it than this, but this is like a dummy, naive one. You understand what I'm saying? So the scenario is the following. You have four keys, right? you know, you are trying to fill a memory. So every time you will write the information you would like to fill, you will push the button, you will select which location in the memory you would like to write, you send the message, then you know it will be written in the designated area in the memory. Then the memory is already full, right? After that, automatically the serializer will be taking this data into a big register like this and start pushing the sequence. Then you know this one is also acting like a ROM, read-only memory, right? It can be read-only memory. You can make it also like a bunch of switches as well if you want. You know what I mean? But you know, let's stick with something simple. It's already stuck somewhere that you know I'm looking for the pattern 111, right? And then you know every single cycle, this will be compared with part of the sequence. Once you will find match, for instance, like 3 consecutive ones happening, then you know you will issue one for the output. That one will be going here, ended with something already enabled high, then that means the output is 1. That means the counter will be incremented by 1, and so on. That makes sense? So what is, from your point of view, what is the object of, what is the final target of this lab? I need to hear from you. What do you think, guys? You know, why I'm actually giving you this lab?
Working with the memory systems?
Huh?
To like understand working with memory systems.
That's one thing, memory system. Okay. Anybody else have to learn to correctly implement the memory? That's something also correct. What else?
Finite state machine.
Huh?
The finite state machine.
Finite state machine is correct. What else?
Well, as you mentioned, the serializer as well.
Serializer, yes. Okay. And the most important part, integration. System integration. System integration. So far, in all of the classes you already have been taken, so far in all courses you are taking pieces. But you never seen pieces put together in a big picture. And I noticed from the previous labs, you have some difficulties with putting pieces together. No, I'm not saying a certain person, I'm just saying in general. There is some problems with integrating things together to make a bigger picture. So this lab is one of the series until we will finish this course of trying to push into the point of that, you know, Verilog is not just building multiplexer, demultiplexer, and you know, decoder, encoder. Is basically fixing a huge problem, using these pieces together like puzzles, and then putting them into a big picture. Then you know you are introducing a new solution. That makes sense. So for instance, you know, here inside this guy, we spend the time of putting decoders, putting, you know, digit decoders, making encoding, you know, making timing select, multiplexing, when, you know, we said, you know, the timing will be cutting between the digit to the others, and so on. So we build a small system. Then, you know, this by itself, it's a finite state machine, as Rohit and, you know, Danush mentioned, right? Then, you know, memory, like, you know, Rohit also, and, you know, Ashley, maybe, I don't know, one of you guys mentioned that, you know, it will be a memory thing that, you know, we need to learn. Then, oh, you know, what about if you, you know, serializer, as one of also you mentioned, then, you know, the last thing is going to be what? How are we going to make this talking to this, talking to this, talking to this without having any problems? So that's called what? Integration. And our target is called fully synchronization. So that means, you know, when I'm writing my test bench, what exactly I should add checking? I have to check the time of receiving the signal. So our target, you know, while we're writing test bench this time, it's not just writing test bench, hey, 1 and 0 is coming out, you know, it's the timing. Like, you know, when this one will bring 1, how many cycles it should wait until it will go here, so it will turn on this guy, for instance, you know? Or, you know, how many cycles it should be taken for this memory to start sorting data from the parallel shape to the serialized shape until, you know, everything will go like, you know, smoothly one by one. Do we need to use something that's called pipeline? How many of you heard about pipeline? Anybody heard about pipelining? So, Christian, what is pipeline? It is kind of, but you know, let me tell you a story about pipelining. So imagine the following. Imagine that I have a block here, it's called stage 1. I have a block here, it's called stage 2. I have a block here, it's called stage 3. I have a block here, it's called stage 4. And I have this packets of data I would like to process, right? Here's like, you know, let's say let's say 1, 2, 3, 4, 5, 6, 7, 8. Normally in the naive implementation, I take this one, I push it as an input here, and I wait until the output will come here of this. So basically, let's call this D1. This is called D executed 1. Let's say the time here is called T1, T2, T3, T4. Okay? Then this one is called D2. So D2 is coming here after T1 plus T2 plus T3 up T4. D2 will be taken into consideration. Then DE2 will be coming after twice of this. So gonna be DE2. Then, you know, D3 will be going on. We're gonna move to gonna be 3 times of the DE3. Then the fourth, fifth, up to the end. Do you think this is a time consuming or not? It's a time consuming. You know why? Because imagine every time this packet, it has to visit all of those lines, while those are actually waiting, doing nothing, idle. Do you agree? That makes sense? So the best way to do it in the pipeline is the following. We will look to the speed of every single one. So you already have T1, you have T2, you have T3, you have T4, right? So what you can do, you can actually give an assumption here. So let's say T1 is equal T. T2 is equal 2T. T3 is equal 3T. T4 is equal 4T. So that means all of them in a unit of T. Okay? Pipeline will assume that you're gonna run with the slowest one. Which one is the slowest? T4. So 4T. Okay? Then what you're gonna do, you're gonna take the D1 and you will process it with the ST1. But in how many minutes? In a 4T. Then the output of this will be the DE1 ST out. Then this will be input for the ST2. So while the ST2 is working on this DE1, the DE2 will be processed by the ST1. Also 4T, 4T, 4T. That makes sense? So by the end of the day, you're gonna spend 4T, 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 4T in the beginning of the filling how many? 1, 2, 3, 4, right? And after that, every 4T, there is an output will be coming. There is an output will be coming. So it's no longer you are waiting for the whole entire what time. It's gonna be just like, you know, latency in the beginning, and then, you know, every stage unit, you will be producing output. That makes sense? Does it make sense to everybody, or should I repeat?
It makes sense.
Christian. Sure, maybe I can clean it in a better place. So here, ST1 is running in T, just T. ST2 is running in the 2T. ST3 is running in 3T. ST4 is running in the 4T. So 1, 2, 3, 4, right? Now, because I don't want something to happen, it's called hazard. Hazard. What hazard mean? I don't want, for instance, this take T time, and I will go ahead and run it T time. Then, you know, I will give it to this one, but this is 2T times, and I'm gonna push data from here so that somehow the data will be stuck in the middle for 1T, right? So in that case, what I can do, I can say I have packets of data. It's called D1, D2, D3, D4, D5, D6, D7, D8. So those are the packets of data I'm trying to process, right? So now, you know, D1 is taking 4T time. Second, D2 will be processed by the ST1. That's ST1, ST2, ST3, ST4. Now, this one will be finished by ST1 and they're gonna be here in ST2. So it's gonna be D2, T2. Then after that, you know, the D3 will be here, D2 will be there, and then, you know, D1 will be there. Then the fourth is gonna be D4, it will be here, D3 will be there, D2 will be here, D1 will be there. Then what will happen? Somebody tell me, gonna be here D5, D4, D3, D2, D1 is out. Finished, right? Then, you know, D6, D5, D5, D4, D3, D2 went out. Then, you know, D7, D6, D5, D4, D3 went out. Then, you know, D8, D7, D6, D5, D4 went out. Have you noticed? So what happened? Until here, we didn't take anything out. Then, you know, every single unit of time, we are taking something out, right? Then I'm done, right? So I can do something it's called draining. You guys do you know draining, right? You know, imagine that you already have a pipe. You keep pushing the water in the what's called in the tube for, like, you know, feeding the plants, whatever, right? Then, you know, you turn off the water, right? While you are unplugging the thing from the fountain, right? What you do, basically, you know, there's still water inside the tube, right? So you have to like shake it like this, then, you know, the whole thing will go out. Then, you know, you just like, you know, roll it up and then, you know, put it aside. So, you know, the smell will not come out of it, you know, or any kind of mold will not be inside, right? Same thing, you know. Now I have the tube, right? I already finished everything, but I don't have anything else to do. But I have to produce those outputs, right? So what should I do? I should drain it. Draining, that means I shake it. So I can push D5 in a 4T, then, you know, D6 in another 4T, D7 in another 4T, D8 in another 4T, but there is no more data coming. So that's called streaming process. That's called what? Streaming process. Doesn't make sense? Or it makes sense? So streaming is important, especially you are doing some craziness stuff. Like, you know, what is crazy stuff you can do? Either that you are working in something that's called multi-clock domain. How many of you heard about multi-clock domain? So in a multi-clock domain, you have a circuit is performing in X megahertz, and you have another circuit is performing in Y megahertz. Okay, so in that case, if those guys have to talk to each other, somehow we have to have something here in the middle, which is called buffer. This buffer, this side will be with X, and this side will be with Y. And that's called double buffer. So you need something like that, right? Our case here in the lab, it's very straightforward, right? This is 4, 4, 4, 4, 4. What I can do, I can, with the pointer, same pointer, when I read out, right? What I can do, somebody tell me. I can just say that, pointer 0. Then in 4 cycles, I will cut this 4-bit to be what? Bit. Then immediately I will feed it to who? I will feed it to this guy. Do you guys agree? Then in the bit number 4, I will increment the pointer to jump here. Then I will start bit. Then I will increment it one more, then, another bit. Then, incremented one more, another bit. Then, incremented one more, one bit, then that would be done. That makes sense? That's one way. The other way is to use whatever we're going to learn today, which is called FIFO. So you're going to be called what? FIFO. But before I go with FIFO, I want to tell you the whole entire idea of companies is not just learning encoder how it works and decoder how it works. It's how can you use pieces together to build a bigger system. You have to learn it from now. We have to focus on this now. We have to do it now. There is no other time you're going to learn this. Is it clear? I believe that, also you guys are in thinking of getting internship or something in summer, right? For those who will not be graduating soon or something, right? So that stuff will give you internship. Because, internship, they're going to give you a real project. And this real project, you have to work and you have to perform and you have to deliver on time. So now, is lab is clear?
Sir, I had 2 more questions.
Sure.
So regarding the memory, since we have 8 different locations, can the user select which location to store the data in? Should that control be given to them, or is it like, FIFO?
It's up to you. It's up to you. I mean, have you noticed, it's called a design course. So in a design, the professor or an instructor shouldn't give the students constraints all the time, because, if I constrain you, it's going to be more not into design. It's just more into just practicing language, or syntax. But, I want you also to be a designer. So, in that case, I would like to give you some flexibility or freedom so you can pick whatever it will fit you from your point of view. You already had a sense since, lab 1 till now about, we are looking for optimizations and power and all of these things. The best way to do it is, to put this in your consideration. I want to achieve low power as much as I can. Do you think that will fit? If it fits, move forward. That makes sense?
Yeah, that makes sense. Yeah, I just wanted to clarify, since you grade by the constraints. But yeah, and then I guess the other question would be, in your video, you said that once we detect our sequence, it would start incrementing.
Yeah.
So that's what you mean, right? It'll keep on incrementing once it detects the initial sequence.
Yes. Every time the detector will bring one, automatically the enable of the entire system where you already have will be incrementing.
Okay.
Unless you would like to play, if somebody play with you on this, one second, sorry, here, right? If somebody trick you and make it down, right? So every time you're gonna increment, it's gonna be decrement, right?
Okay, yeah, that was my next question. Yeah, so it can also decrement as well. Okay.
That makes sense.
Yeah, that makes sense.
Because
and then, for example,
because think about it from the other lab perspective. I might ask in the future, right? Imagine that we can have two different sequence detectors, one for the incrementing, one for decrementing, and then you are pushing from the two sides bunch of data, right? So they are in fight, right? One is incrementing, one is decrementing.
correct.
Right? And who will be the winner?
Mm-hmm.
That's called K-map bioinformatic concept. Okay, so like you already have two sequence, they don't know each other. Like we have monkey and we have lion. This is a DNA and this DNA, but I would like to see what is the similarities between two guys, right? There's some similarities somehow between of them, but it's not really high similarities, right? So you need to check who is the winner, in terms of like the gene for eating I don't know, eating grass, or drinking juice, or I mean something, then you have to start doing this with a bunch of DNA segments like ATCGA, whatever, from both sides, and then you come and say, oh, there's similarities between two creations, even those two guys not from the same species. Something like that, you know what I mean? So, you said you have another question. What was the second question?
Would the output flag of the sequence detector, can it be reset by anything else, like an enable or a disable switch, like a universal one?
Yeah, you should have a master reset, right?
Correct.
You should have a master reset that when you click on it, everything will be reset.
Mm-hmm.
And you should, that's something you have to think about it. Or also you can have like a reset bank if you want. What does a reset bank mean? That means the monitor and this area should have a reset, since they are just like a place telling us what is the similarity weights, right? So they should be clear by themselves, while this guy also should be clear by itself, right?
Yeah.
So that means either you can have a master reset, or you can select which pieces can be reset. In that case, you need a kind of like a bank of resets.
Okay, yeah, fair enough.
Yeah. Any other questions? Chad, do you have any question? Louis, do you have any question? It should be our last lab, yes, because we need to start working in the project. We're supposed to have 10 labs, but because we were waiting a lot for. Do you remember when we were waiting for everybody to get the FPGA? And then one lab I extended twice, and then this lab I actually made it 2 weeks. So there is a quiz on Wednesday, but we don't have the lab delivering on this Wednesday, right? The lab that's gonna be in the Wednesday after, right? So I give you 2 weeks to think about it, because the whole entire point from my perspective and from your perspective is to be like, what is the best way to learn? The best way to learn is to work on the thing. You start getting errors, you start debugging. Something is not clear, you come back to ask, and so on. That makes sense? But do your best, because I'm trying to increase your degree of freedom. That means I would like to increase more and more. So you ask more questions, a lot of questions in the first couple of labs. Then you start asking less questions in the third and fourth. Then you started less and less and less. That means that the degree of freedom and the independability of you is actually increasing. That shows that how you are very good designer. That makes sense? Okay. So now I'm gonna tell you a story about the FIFO. Maybe we can look at the code together, and then you will be released, because I know that you already have a lot of midterms this week, right? I think so.
Yeah.
I don't want to be too much on you guys, so that's the whole idea. I'm trying to be reasonable. Yes. So we mentioned that we have 3 different things we need to put in our consideration before we officially say that we are done with this course, right? We said we need to learn what is FIFO. We need to learn, after we use FIFO, we learn the PLL. We learn how to use the clock dividers. So we're gonna put them together into something that's called UART. So now you can actually use your C language experience for pushing streams from the computer through the UART, hold it by FIFO, and then you go into sequence detector or whatever, and then it will be memorized and recognized on the digits. Then we said the third or the last part. There is one more a finalistic machine example I can give you, which is basically a traffic control light, but it's a piece of cake. But anyway, the last part I would like actually to share with you is going to be the VGA. How we can actually make the VGA driver using Verilog. How are we going to make the screen in front of you connected to the FPGA board turning on? We don't have a processor for like running games and so on, but by learning the UART, the VGA, while also you are getting more experience using the integration stuff, with FPGA, you will be able to work as a group for the final project. That makes sense? And the final project will be, I don't know, maybe in a week or 2, then, until the rest, and then you will show it to me and you will get the portion of the grade based on the syllabus. And that for the 10 labs, I'm gonna be redistributed. But this lab, the lab is coming, it will have more weight than the rest of the other labs, since everybody's mature, Okay. So the one in the series we need to learn is called FIFO. So let's naively describe what is FIFO. And from there, we try to think together as a team, including myself and you, how can we build, how it does look like, you know what I mean? So the FIFO is like a black box like this, okay? This one, it has a kind of a memory. In this memory, of course, you have a kind of a clock, because you would like to decide at what time you can pick data out or you can push data in. So we need something to give us time. So that means, it's a sequential, right? Do we need to reset location in the memory? I don't think so. But we can use the reset for resetting the first output, So we can leave here a reset for the moment, okay? Then we need also an input streaming going to the block. And we need an output coming of the block. So that's basically an input. And here's an output. Then we need some little itty-bitty flags to define to me what is the current status of the certain device. So for instance, if I use all of the location inside this block, I have to inform the user that I'm in full. So that means I need full flag as a status flag, telling me that I cannot put more data into this device until something will be cleared up, right? Then I need another flag, is called empty. And this flag empty, when I'm empty, that means all the possible location inside this pipe is completely empty. What I'm gonna do, I'm having the luxury to push inside the device. Then I need two things. I need one is associated with the input, and I call it push. And the job of this push, it will be every time I make it high, that means whatever written on this bus will be literally moving inside the memory. That makes sense? Then I will need also literally another input, but it's not associated to the input, it's associated to the output. It's called pull. So every time pull is high, an output will be reported from the device. So that's pretty much what is called FIFO. Does it make sense?
Professor, is pull the same as pop in terms of like stack?
Yeah. No, stack is different. Stack is LIFO.
Like as a comparison, like I know they're different.
You understand my point, right?
Yeah.
But in general, yes, it is. It's like basically you already have a multiple locations, and you pull something, you push out. Yes, exactly. It's the same, but it's from a different family, It's a buffer, but it's LIFO,
Okay.
So everybody agree? So the pull depends on the empty flag and the push depends on the full flag. Kind of. Okay.
What does the pull do again? Sorry, Professor.
The full is just a flag.
Oh, the pull.
The full is a flag saying that I cannot take more data.
Oh no, I meant the pull with the P.
The pull, I'm sorry. The pull is actually taking order saying that I need data to be coming out from here.
Okay.
I'm pulling data.
So it's like a pop.
And pop, yes, I'm popping out something.
Oh, okay.
Okay.
Wait, so you said the pull is resonates with the full, and then the push resonates with the empty?
No, what I said is the following. Push is just like, I can think about it as the following. If I find empty is high, that means I don't have any problem to push. Right? Because there is nothing inside, right? But if I see full high, that means internally I believe that I cannot push anymore until this flag will go down. That means there is another location I can, it can host my data.
Okay, got it.
That makes sense?
Yes, thank you.
So one of the possible design I can have, it can be based on the memory I give it to you. Do you agree? So the memory I give it to, it was like this. N bit. And that was the PTR, right? And what was the PTR read, right? And that was the write enable, and that was the read enable. 1 second, let me check my 3D printer. It's doing something anyway. So
you gotta auto level the bed.
Huh?
You have to auto level the bed. The print bed.
It's annoying. I hate it,
What are you 3D printing?
Something for a project. Tristan knows, right? It's our motion controller. Okay, so anyway, no, but what I'm doing now, I'm just this is a new printer, I just bought it and I assembled, but I didn't have time to use it, right? So I spent some time on adjusting temperature, adjusting the bed itself, all of this trick about you have to use a thin piece of paper for taking whatever and all these things, adjusting the type of the filament I'm using, all of these things, So it took some time. So now when I'm printing what's called a cat, just like, to test whether that is working or not, If it works, then, I will start printing the box for the motion control. That's something, Anyway, back to the point. So now this gentleman and this gentleman and this gentleman and this gentleman is our manuals, right? Our manually exist. Do you agree? What does it mean manually? That means I have to put by my hand right enable. Then I have to start incrementing the rights. 1, 1, 1, 1, 1. And every time I increment, the data will be located, right? Do you agree? That makes sense? Everything gonna be clocked. I will tell you why. Anyway, need to be tied to the clock for its automatic. Exactly. So automation is gonna be different. So basically, you will need another box which is called in directions, and this one, for instance, might have a start. Oh, you know what? I don't want everything to be start. I can just make it like more fun. So gonna be here still clock. So this clock will be connected to this clock. Then I need here also master reset. Then that input is gonna be push. This input also gonna be pull. Then two flags here is gonna be what? Empty. And they're gonna be full empty. And who will be the output? The output will be this guy and this guy. What is S just ended? What is it? This is ended. Okay? And that will be our finite state machine. So we need finite state machine to work as a wrapper around our memory that we learn. And of course, this is an input and this is an output. And that will be our Fifo. Is it clear? Now we're gonna move to what is exactly will be inside what, all right? So I can draw it in a different way. So look, I didn't even write any piece of code. So that's showing you that, when you will look to spec of anything, you have to think about it and you draw it and you will just digest it before you will start writing, right? That's a straightforward thing. So, what we can do, we can actually make it in a nice way. So we can write it in a nice way. So we can make this block of memory. I made it up here. This one, I can call it like this, and I call it what? Dual port memory array. Why dual port? Because basically, we have input output, right? So I can push, I can get the data from here, and that will be what? Write data, while this what? Read data. Then I said there's an read address, and I said here there's an write address, right? I should have here a unit for this. Is called the read pointer, and I should here have what? Write pointer. Then I will compare between of them. So I will go here and make a comparative between pointers. So compare logic between this and between that. When I compare between of them, I will go ahead and do what? I define my flags, which is empty and full. That's it? Nope. We will need a kind of interface like this, and we call this write interface. This write interface is taking data and also pushing some order to the write pointers. And we need also from this side, we need another interface, and we call it read interface. This read interface will be also controlling the read pointer and taking data to be presented outside. So you can just like get it up to be read data here, and you push it here to be what? Write data. Just like, hanging wire out. And then, you have here the write enable. And you already have here also what? You can take this out to be official full. You can extend this out to be what? Official empty. So this is basically the way of describing what we're gonna write as a Verilog code. Okay, so we need to describe this, describe this, describe this, those guys, and then we combine them together, by initializing them or initiating them, in a top file that will be the Fifo itself. Is there any questions so far? Any question? Okay. If there is no question, can you go over the interface again? Sorry. Yes. So basically, we need a kind of controller from outside, right? Do you agree? What is the controller from outside? Something will take those signals into the consideration. Something will be in and out, something will be in and out, right? So what is basically the in and out? When you say interface, do you know what is I/O? It's just like wiring, or how to say, extending wires. Interface is just a bunch of wires. You know what I mean? So that means those guys has to be extended out here to be official names. Those guys will be extended here to be official names. And that will be our thing. Why do we need the compare block? I will tell you why. Because every time you pull, you have to decrement the push. Because you already took data out. So you have to compare, right? Think about it, right? You already have 2 pointers, right? Imagine the first scenario. First scenario, you will start incrementing the one is actually writing, right? 1, 1, 1, 1, 1, 1, 1, 1, 1, whoop, you reach the maximum of it. When you reach the maximum of it, what will happen? You cannot extend more, right? So the full flag will be high, right? But when you are pulling, you're actually what? Decrementing the push. Does it make sense? Michael? Michael? Oh, I will tell you. Look at this. Don't worry about memory or anything. We have here location 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 7, 8. Those are the 8 locations we are actually taking, right? Do you agree with me, Michael? Now, I'm pushing data from here, and that's will be data N. And I'm getting data from here out. So far, so good? Look, now, my pointers is pointing to this location, right? So that means, officially the data, this data D1 is coming to be written, right? So, the pointer now is in location 1. So basically D1 will be here, right? Then the next, that will be incremented to go here. So the data D2 will be written there. And then you push, then, that will go there. So it's going to be D3. You push, they're going to be D4. You push, they're going to be D5. You push, they're going to be D6, right? You push, they're going to be D7. You push, they're going to be D8. Can you push here more than that? You can't, right? Till now, I didn't take anything out here, right? So in that case, if I reach this point, but, my pointer here is still up here, and I didn't even activate it, so I have to compare. In that case, I can say full is high. Now it makes sense? Now, this guy, while it's moving to pull data out, this one, it has to be decremented. Because, I already take D1 here, right? No need for D1 anymore, right? So that means, I can welcome anything to be written in this case. So that means I have to decrement. Every time I decrement. So literally, I'm not gonna tell you, that, oh, I'm gonna invent something for you. It's an internet. Everybody can look at it in internet. There is no problem, So I can even share with you something I found in internet. Because all of these blocks are well known for generation after generation, So I'm gonna share with you something I found on internet, which is really, very interesting, Here. Can you see my screen? Everybody can see my screen? Yes. So look at this, right? Here is basically what we said, I have here the dual port memory array. Here's read data. You're gonna just extend it out here. Here's the write data coming from there, right? It's just like a wire moving there, right? Then, the interface, I have to enable the writing. Then, I have to figure out whether that I'm full or not, or empty or not, right? Here is telling you the story I was telling you about you push and, you pull and all of these things. But, how you can make a code for this, that's not really hard. There is 10 to 15 way of making your FIFO. Okay. One of these things is actually to use IP. Like you generate an IP from the Vivado with a semi-specification, you run it, everything would be perfectly fine. That's one way. The second way is actually to write your own code behaviorally. Or there is other, when you say behaviorally, there is 10 to 15 way to design. Then you can make it structurally. How many ways you can make it? You can make it up to 25. But we're not gonna go through all of them. We are not gonna make a PhD in FIFO, I just want to let you know what is FIFO and how it works. So look at this. This guy is using define like I told you before. And I asked you in the lab, and be sure that to use it in the lab, especially with test bench, with the time steps. Make your test bench more generic. So you use the define. So did you see what he said? I define my buffer because he considered the memory a buffer. Do you guys agree? The memory is a buffer. The size of it, the size of the buffer are 16s, but the bus width is 4. Okay. So in that case, I'm gonna take this one with shifting operation we learned in the beginning of the Verilog to define the buffer size. These two steps made the buffer size equal 16 as a parameter, not parameter, constant. Okay. Then these two guys later we will call them in where in the body itself of the FIFO. What we are expecting as an input output to the FIFO. So we are expecting the clock, we are expecting the reset, and we are expecting the data in, which is the buffer in, and we are expecting the data out, which is the buffer out. We are expecting also write enable, and we are expecting read enable. We are expecting that this buffer is empty and this buffer is full, and we can actually make extra external counter telling us where exactly in each row we are standing. That makes sense. That's a luxury. That's an extra thing we can do. We can actually remove. Then we define here input and output. Have you noticed something? This example is using the old way of defining input output ports in Verilog 2001. But we learned before in this course that you can just go and say input clock, input reset between the parentheses, right? So you will do all of these steps in one shot. Do you guys agree with me?
Yes.
Okay. Now we have to define extra internal info, like a register, right? So for instance, we are not having here my memory and you're putting in, he's gonna build the memory inside this as well. So look, so he defined the reset. All of this are single input bits. So basically he put them in all of the one line. And then with the buffer in, he decided to make it restrict to 8 bits. You can also make him a define and you can define it, that's perfectly fine, And when you define it here to say buffer data width, you say 8, then here it's gonna be what the width -1 to 0, because it's a 7 to 0. So here he defined the input, and then he defined the output, and literally for sure later on he gonna make it register, right? Because it's a memory. Look, he called it here output, but then he called it again register. We learned before that we can say what output and register, right? So this small line to be used. Also, the input empty buffer and full buffer, in the draw that we use in the tablet now, we said those are the flags, and we say flag, that means they are outputs. Do you guys agree? And because they are outputs, basically they have to be also registered, because they have to store data. Then the counter, it's a counter, so it has to be a register, And what is the size of the counter will be the locations we have in the FIFO. Do you guys agree? The location we have in the FIFO. We define in the beginning how many locations we have in the FIFO, 16. So we are here telling this FIFO counters will be 15s to 0. Somebody will tell me, oh, but you said, it's gonna be 16s -1 to 0. No, in a FIFO we will have an extra one for the final reporting, and I'm gonna show it to you. Then, but the pointers are the pointers. They're gonna be, those are two different things. We are defining them now. They are not exist in the in and out. They're gonna be internal. Why we need them? For this arrow and that arrow when I go in a compare logic. So look at this. I call it read pointer, write pointer. What is their size? Somebody would say it's gonna be 15 to 0, because I cannot report outside than that. Why I need this extra one in the FIFO counter? Because it will help me later on with the full and empty. See, so now we are working here in the synchronization with integration. So we have to think about what is our boundaries. That makes sense? Now, the step we did before in the defining the memory block. So do you guys remember when we said when we are defining block, we will go and say that it's called buff memory. And this buff memory, it has every single row is an 8-bit width. While how many of those are in this memory buffer? 16. That makes sense? Do you guys agree with me? Hello? Now, look at this. Look at this, which is basically what I said, right? When I see FIFO counter true, huh? What do you mean? Buff width? Yeah, I mean the size of every single row inside the memory is 8-bit. The depth is 16, but every single row is 8. That makes sense? Oh, okay. Anyway, now I want you to think about this. Now we are using the beautifulness of the language. When I said like this, at always FIFO counter, so that means I'm looking for every movement of this counter. Then whatever inside of the block will be what executed. Have you noticed? So every time the counter will be processed, I will be sure that buffer empty will be equal what? Will be equal 1 when FIFO counter equals 0. This is the way of writing it. Look. So basically, when FIFO counter equals 0, be sure buff empty to be what? 1, to be high. And be sure when the FIFO counter reaches the 16s, the buff full will be equal what? 1. This is a way I didn't show it to you before, but it's actually in the old generation Verilog. It's still used, by the way. You can make it with if statement. Do you agree? Do you agree? You can come and say that, if FIFO counter is equal 0, then be sure buffer empty is equal 1. Else, if FIFO counter's buffer is equal size, then buff full will be equal 1. The empty will be 0. You know what I mean? So case statements you can do, or you can just do it easy, lemon squeezy like this in a logical way. So these two lines told us, what is the boundaries we can ever see. When the FIFO counters will be touching 0, empty is happening. But when I touch the ground of the buffer, the full will happen. Then now we need a logic. We need some logic here. Look at this logic. This is the most important logic we need. What is this logic is? This logic is fully sequentially. So that means, I'm going to use the clock or the positive edge of the reset. And in that case, I would say, if I'm resetting, my counter is actually initialized by 0. But then look, if I'm enable writing, but the buffer is not full, if enable writing, that means I'm trying to write, and at the same time, the buffer is not full, and at the same time, buffer is not empty, and I'm also pulling data out, that means reading enable. That's actually one of the cases can happen, right? So in that case, I will do what? I will keep my FIFO counter as it is. Because, every time it will increment or decrement. So at the end of the day, going to happen that, I don't need to increment or decrement. That makes sense? That's the compare part. Do you remember when we said there is a block, it's called compare? Yes. Then there is another possibilities, which is what? I'm writing, but the buffer is not full. Then I have to do what? I have to increment the counter. Have you noticed this guy is not using 2 pointers? This guy is actually using 1 pointer for read and write, which is called FIFO counter. Do you agree? Anyway, the third possible case is basically if I'm actually pulling data out, but I'm not empty. So what I need to do, I have to decrement the FIFO by 1. So one of the case, I'm reading and writing at the same time, and there is no empty, there is no full. Just keep the FIFO as it is counter. Because at the end of the day, when you increment and decrement, it's gonna be the same. But if those 2 guys didn't happen, and I'm just like in the buff full is not empty, and I'm writing enable, then I will increment the FIFO once. But if I'm in just case of that, I'm pulling data out and I'm not empty, I will decrement the FIFO by 1. Other than that, keep it as it is. So this is the brain of the FIFO. And we finished. Now we're gonna move into the time of pushing data, the memory, right? So I said my reset will be just resetting the output thing. It's not resetting internally inside the buffer. But you know what I'm saying? If I am not empty and I'm actually pulling data out, so literally I'm asking you to do what? To take the read pointer and do what? And pointing to whatever will be written in the out. Else, keep it as it is. By the way, you can actually remove this, but normally you will open the door in front of what else will happen. So, you keep it as it is. You know what I mean? Just like for, while you are writing, so you will not forget. So pretty much this is actually the mechanism of actually pulling data already out from the buffer. Now I'm gonna go into the reverse. What is the reverse? Look at the reverse, which is fun. The reverse is here. I'm clocking, and then if I am not full and I'm actually writing, what will happen? So the write buffer will be responsible to pointing which location inside this FIFO will be hosting the current data written in the buffer end. Other than that, just keep it as it is. Then I never say what is write buffer, read buffer. I just mentioned FIFO counter. So what I'm gonna do now, I'm gonna start using the last part of reducing the actual write and read. So look at this. Write buffer, read buffer in this case, they will be reset when the reset master happening. Then if I'm writing enable and I'm not full, what will happen? I'm gonna increment my write buffer, else I will keep it as it is. If I'm reading enable and I'm not empty, I will increment the read buffer, else I will keep it as it is. By the end, I'm done with the whole entire implementation. So is it clear to everybody what I mentioned so far?
So essentially, this is a behavioral approach to creating the
Yes.
finite state machine, right?
Yes, that's one of the way to make a finite state machine is basically to use, because if statement is actually case statement, if statement, all of those guys are actually from the same family, right? It's a family of decision. So you are decision making something. You are making decision based on what?
Isn't the code is just a big truth table as to like
kind of
what you're right?
Kind of. But the whole entire thing, have you noticed you cannot write this code without fully understanding what's going on inside, right?
Mhm.
So that's actually the way of thinking, we are no longer here thinking about, oh, I didn't take this syntax or whatever. We are more into higher than that. We are looking into what is my problem. I have to analyze the problem, putting a realistic specs. And from there, I will go ahead and start using the syntax I learned. That makes sense? Then the guy, he made some fancy test bench, and look what he did. He used also the find in the test bench. And he used something in a test bench, which is already in test bench, but I didn't show it to you because, we are not in a verification course. So, there is something that's called pop and push. You push and pop, you push and pop. Those are actually something that's called task, subtask, and a verification. But the course we are taking is not verification course. So I might actually go through it with you next time. But, the most important thing for me is actually you fully understand this code, and also you try to map this code onto the memory thing that I give it to you, which will help you actually to resolve the lab, the current assignment in the lab. Any questions so far?
With the defined statements at the very top of the code, all that buff size 1 shift operator buff with is increasing that 3 to a 4.
Yes, this one?
Yeah, that line.
Yeah, that's the depth one. So basically, if you have here 3, that means, you push it 3 times, it's going to be 4. It should be 4.
Oh, okay.
Yeah. 3 to 4, yes. When you push, because the last one is going to be the corner, it's going to be 4. Yes, it is correct. Okay. Sounds good? Any question? Do you guys have any questions? Okay, so I actually can give you this link as well. Everybody can see the link in in the chat, right? So here's the link, and also the recorder, so you can look at the recorded lecture. In that case, I would say that, now it's a time just for what? Practicing. So I will let you practice today, because I know that, Wednesday you're going to have what? The quiz, right? And
is the quiz is the quiz 1 day or 2 days or
1 day?
1 day? Got it.
But the quiz is going to be the following. This time I'm going to go into the quiz. The first 10 minutes, I will read the quiz with you. If you have any question, I will answer.
Okay.
About the question, if anything is confusing you, whatever, into the quiz. But I'm not going to answer, of course, the quiz. But, at least, is there clarify any possible question you can have? Maybe you can have a half an hour discussion. That's fine. So that means, you will not waste your time of like sending emails, waiting for me to reply and all of these things. You know what I mean?
Mm-hmm.
I don't want to kill your time. That's basically what I'm saying. And also, I don't want anybody to get confused. So basically, we're gonna go through the questions. We're gonna go through all of the stuff that you might have. Other people will hear it as well. Maybe they will not put it into consideration, but later on they will ask and so on. So it will be repeated questions. So we'll cover everything. You will go ahead, do your practice. You will put the stuff on the grade scope. I will grade it automatically. It will be posted to you.
Is the quiz being released at 11:30 or
the quiz will be released 8 in the morning.
okay.
Is this quiz on the whole semester or recent content? It's gonna be the whole entire thing. And this course is accumulative. It's not just like a pieces. Okay, so you mean entire semester? I mean, yeah, I mean until now, you know, from the beginning. Yes, yes. Because we haven't finished the semester yet. You know, what time are you reading over the quiz? Yeah, I mean in the lecture lab, in the lecture or the lab time. But you know, I'm gonna release it in the morning, like last time. So that means, you know, that you're gonna be the same day. It's a quiz.
Hmm?
You know, it's not midterm. Midterm is different. You know, it's midterm. You know, midterm is more questions. You know? Okay.
It's due Thursday at 8 a.m.
And then if let's say that your grade in the quiz 2 is way better than quiz 1, what will happen? Your grade in the quiz 2 will be taken over the quiz 1. That was our deal, right? But if you get in the quiz 2, a grade is not that's really higher than whatever you got in the quiz 1, then both grades will be added to each other. They're gonna be case by case.
I do know sometimes, Professor, you like to make a late due date on Gradescope. Is that applicable only to your midterms, or?
I do it for the people who are actually outside the United States.
Oh, I see.
So some people, you know, because of the COVID-19, they are actually outside the United States. They're in other continents.
So
the time
there's
difference is really huge, you know.
So there's the due date at midnight Wednesday, and then of course there's that few hours later late due date.
For them, yes, for them.
Yeah.
But you know, if you have something urgent happen, you know, and you justify it to me, you can go with them in the late. Okay. Sounds good. Any other question? So what is the next lecture going to be about? UART. And how can we use the UART? How can we transmit and send data through the UART? We're going to use the FIFO and we're going to do the work on it. Now, I'm going to share with you something else before we leave, which is basically how can you create a FIFO using what? Using Vivado IP. That's another story. Okay. So at least we learn how it works. How can you build it? You already have the link, and also you already have a recorded video of this, so you can see how can you read it, and you know you can play with it. It is fun to do something like that, and also you're gonna learn how can you break it up, which will help you to do the current assignment. You know, I'm sorry, my Vivado takes forever. You know, I don't have that much area left.
Is it just one singular IP or is it multiple IPs?
It's one IP. So you know, if you look, I just have 35 gig left in my computer. So so you know, it's completely hard for me to generate anything. You know, so everybody can see my Vivado?
Yes.
Okay, so let's call it what? FIFO? FIFO IP. But this is not the motion controller project. That's basically our what? I forgot. This one, right? Let's call it FIFO IP. ECE3300 TCS -1 right? Finished. Okay, everybody can see it now. So you guys see my screen, right? So I'm gonna here in IB catalog and say I want what? FIFO. So there is a ton of FIFOs. Some of them belong to the AXI bus. How many of you heard about AXI bus? I'll just go Fifo Generator. And from there, I click on it. Here is my Fifo. I would say it's native, so that means it's not using any AXI. And look, do you want to use the block RAMs for implementation, or do you want to use lookup tables or shift registers or built-in Fifo or block RAM with independent clock or distributed RAM or built-in Fifo with independent clock? So see, give you a big luxury, right? Because you can read in a clock and you can write in a different clock. You guys agree? Like for instance, in this example, look, this line, right? This area, right? It can be in a clock, and this one it can be in a different clock. So I'm pushing data in 100 megahertz, and I'm getting data out of this buffer in 5 megahertz or 500 megahertz. Those are completely independent. That's what they call it, independent clock. So here, let's say that I'm gonna take common clock. That means the input and output will be using the same clock source. Okay. Then it's telling you, do you want it the error correcting code or you want stuff like that? That's not really a big problem. It's not a problematic problem. Then I would say it's native. Then I said standard FIFO. What is the write width you want? That means how many bits it should be. Let's say 8. You have up to 1,024 bits you can represent as a word. After that, you have to make what? Configuration. You guys understand what I'm saying about configuration? That means, I'm gonna bring 4, 5, 5, 4, put them each other together, and I truncate piece of data from one to the other. That makes sense? Hello? Are you guys there?
Yes, Professor.
Do you understand what I'm saying, right?
Mm-hmm.
So that means 501 is taking the bits from 0 to 1023, while 502 is taken from 1024 to 2047, while 503 is taken from whatever. That means you're gonna have a multiple FIFO generated, not just like one bit, one block, and that's it. You're gonna have multiple blocks. Then here's that your depth. Your depth in this up to a big number, basically. So let's say that in the example that we have, it was 16. Okay. Then my read width, it's 8. You have a luxury, by the way. You can say I would like to read 1 bit. See, like the one we said, right? Do you remember the serializer, deserializer? But you are not gonna use the IP. You're gonna use your own code because I would like to see the way you're gonna work with. Here, the actual depth of the read also, because you can make sections. That means I can come and say that I have 4 outputs of this FIFO. One is reading from 0 to 7, the other reading from 8 to 15, and the other is reading from the 16th to whatever, 23. You know what I mean? I can make it like that, right? So I can make it subsection inside the FIFO. There is no problem. Do we need any kind of error correcting? I don't think we need it. It's very pricey in terms of resources. Then do you need a reset? Of course, I need reset. Do you want it to be synchronized reset or asynchronized reset? Somebody tell me, what is the difference?
Synchronized just goes along with the clock. Asynchronous doesn't.
Yes. So when you say synchronized reset, that means when you issue reset high, it has to be coming with a positive edge at the same time. So then the reset will happen. The asynchronized, that means it doesn't matter whether it's actually in the middle of the clock, in the level of the clock, outside the clock, but you made the reset high, automatically it will executing the resetting no matter what will happen with the rest of the FIFO. So in that case, let's say it's synchronized, cheaper. Then the do out text, don't worry. Did you see this? Latency, this is the thing that we learn about pipeline, right? Latency 1 cycle. Latency 1. You know what does it mean? That means that every cycle the output will be reported. Everybody understand what I'm saying? Every cycle the output will be reported. Then the flags that we mentioned, right? So do you want full and empty? There is something also called almost full, almost empty, because it's working based on this FIFO counter, right? You can define that that almost FIFO full, it can be high maybe if we reach 75% of the resources. Just like a warning for you. You understand what I'm saying? If you want, you can just come and say here, yes, you can just say yes. Automatically in the manual, it says that, it is based on the 75 to 25%. But, I don't want it. Do you want acknowledgement, handshake? That means every time you give me a data, I will be reporting output and say that I acknowledge that I get the data. I don't think I need this. I don't think I need this. Data count. Do you want any counter to count the data? I don't think so. You don't need this FIFO counter to be out. It's just internal. And then, here's your summary. So it's summary. I'm going to use a common clock. The implementation will be using block RAM. This behavior modeling. The width of every single row inside this is going to be 8. The depth is going to be 16. For the same size for the read, it's going to be 8 and 16. I didn't use almost full and empty. I didn't use programmable full and flag. That means, I can actually say when it can be full, when it can be empty. I didn't use data count outputs, basically. I didn't use any handshake. I left it to be asynchronized, and hazardness can happen. Reset, it can be in high and synchronized. And latency for reading while the rising edge of the clock is going to be 1 cycle. So I can just double check the status register again and a new port here. And pretty much I can come and say, I don't want this. I can just say yes. Yes. Just say generate. We didn't select it will be Verilog or VHDL, right? I think that's gonna be VHDL. So I need to go back here and go in the setting and see what is the language is there. No, it's Verilog. So it's gonna be Verilog, because see, you can actually select you wanted Verilog or VHDL already. Okay. Now it's taking its time to be generated. So let's see what will happen. It takes some time. Sorry about that. You see that this greenish thing is running? It means that the process is actually taking the right place. Maybe the message about the starting time, closing time, and stuff like that. Look what happened. It used 18 lookup table and 20 flip-flop. And then, you know, half VRAM. There's a story about half VRAM thing I will show to you. But anyway, look, if I go here and I say, okay, there's some. So here is a file that, you know, you can instantiate. It's called Fifo Generator. Everybody can see it? Hello?
Yes, Professor.
Then, you know, I can literally go ahead and click on it, and then I can find here the name. Look, there is a clock, there is a star reset, and it's going to be synchronized reset. Here is your data in, here is your write enable, here is your read enable. And of course, what does write enable as? Going to be push. The read enable is going to be what? Pull, or, you know, pop, or whatever you call, right? Here's the data out, and here's your full flag, and here's your empty flag. You can call it and make a test bench, and you can see how it works. So internally, you know, it did all of this charisma stuff that, you know, with Axie bosses, you don't need it, and you just, like, you know, activate stuff, deactivate stuff. You don't need all of these things. It is HDL generated. That's why it's called read only. You can actually converting it to a writable one. They will not allow you. You just need to take this one. And by the way, this is actually written in what? .vhd. This one is written in .vhd. Somebody will come and tell me how I'm gonna use this is .vhd. You can still call it in Verilog. You can make a new file here in the top, and you call it what? Fifo_Verilog.v, and then, you know, you will make a module Fifo_generator_0 and all of these things to be exist if you want. So let me see. There is a way to do it. It should be Verilog. I don't know why it's generated like that, but we can see Fifo. Where is it? That's interesting. I want it to be enable. Here's the documentation for the thing that you can look at it. IB hierarchy, show of the all IB hierarchy. The status, basically this one. But why give it to me Verilog? Now HDL. There's a way to convert it. So, interesting. Oh, here an IP should be also Verilog. Let me see 1 second. Everybody can see Vivado, right?
Yes.
Okay. So it should be by automate system Verilog. Why is not Verilog? That's the difference. I mean, what I can do, I can just take it like this, copy. I say at source, create the source design, and I will just say create design, and I call it Verilog, and then I say that, going to be Fifo interface. And from there, I can just go over it like that. And I just make it like this, no problem. And I will show you now a trick. But I will find you why it didn't do it. It should be Verilog automatically, but it's craziness. It takes forever to do it, my gosh. Anyway, look at this. You can just go ahead and say this like this. And then, you just go like this, and, Fifo Generator 0 is, right? And then you instantiate it with what? Mem. And then you just make like that. Then you can just go ahead and say, clock SRST. Then write enable and the out and full and empty. Sounds good. Then we'll go here and just make what? Input clock input reset input 70 GN input right enable. Well, let's call it push. I like push. And then and then the out, right? Output reg 70 the output register full output register empty. Then we can literally say bye. Then you take clock. Oh, scheiße. Then push. Look what will happen now. Have you noticed just updating? Because my computer is slow. But what happened? It called this guy, right? But the name is not completely correct. So we need the name, the correct name. So it should be everybody can see what I did? Hello? What I did? I use Verilog as VHDL because all of them from the same family is called HDL, outdoor description language. So now you can take this gentleman and call it to anything else you want. and see the hierarchy. This is written in Verilog and those guys written in VHDL. Any question?
I have a question about the first steps you took to make the IP.
Yes, sir.
You went to the IP catalog and then you just generated it from there?
Yes, IP catalog. I set Fifo here in the search and I found the one I'm looking for. And from there I can move forward. I know that there is a way for you to generate it immediately as a Verilog, but I don't know why. It seems that I have some problem with my interface, you know?
Can we get here this by going through the create block design?
Yeah, I can click again and see. See, it takes forever, you know, it's not even opening. Here it's open. Go ahead.
No, yeah. If you were to start outside of the IP catalog and then you were to create a block design instead and then add the IP onto the block design?
No, that's a different story. You know why? Because you know you're gonna build pieces and you're gonna connect them together. You know, still we are using HDL here, right? That's a different thing. Because you know what you're talking about is completely different. Why? Because what you are doing is gonna be making you're drawing stuff and playing block. Then you have to do something that's called HDL wrapper. Then when you will do the HDL wrapper, then you will return it back to HDL. Then you will start injecting stuff in the code.
Oh, okay.
You understand what I'm saying?
No, yeah.
Because you know, let's say that you already have a microblade as a processor, right? Then you can call it and you push data there. Then you know you will finish the whole entire thing. But I need C microblades as a HDL. Then you know I have to do the trick of the generate HDL wrapper. That's actually a system on chip, SoC. If we have time, I will show you an example of this. Okay? Sounds good? Anybody have any questions? Anybody have any concern? In this case, I can say, I'm done for the lecture today. I don't want to overwhelm you with too much material and resources. I want you to focus now on what? The lab. Learn, use, observe, and get conclusion. Sounds good? Next lecture is gonna be the UART. And the lecture after it will be the VGA, then we'll be done. Maybe some couple of finite state machine examples, and then you know we will be closing and concluding and focusing more into our project. Okay, look. Any question? So good luck, guys, with your midterms and all of this business stuff. I know that it's too much. Do your best, and you know, please, you know, I would say watch all of these videos that will help you. I mean, the good thing about watching, you don't need to literally watching. You know, you can just like scroll back and forth to pick up the information you need. I know that all of you are doing some other stuff besides studying. So do your best, and if you have any questions, I will be more than happy to assist you. God bless you. Stay safe, and I'll see you on Wednesday for a couple of minutes going through the quiz with you. And then, you know, the lab delivery, it will not be this week. It will be the coming week, the week after. Okay? God bless you. Stay safe. Thank you. Thank you, guys.
Thank you, Professor.
Thank you. Have a good day. Oops.